All right, guys, we're going to start our new unit, and it's on thermochemistry. Many of you have already had introduction to thermochemistry. You're thinking thermo heat and how it relates to chemistry, obviously. Goes to his therapist. I have self-esteem issues. His therapist says, well, have you tried going to Walmart? That could help his self-esteem issues. All right, moving on. That was kind of messed up. Energy is the ability to do work or transfer heat. Okay, there's a definition for you. Potential energy, we're going to talk about potential energy, and as it relates to chemistry and matter, we use the term enthalpy. That should be a term you guys are familiar with from your chemistry class. Potential energy is the energy an object possesses by virtue of its position or chemical composition. Remember, all matter has energy that's stored in the matter in the bonds between the atoms that make up that piece of matter. If you had to calculate kinetic energy, remember kinetic energy is the energy of motion. It's 1/2 mv squared. M is the mass, and then v is the velocity. So you see what contributes to the kinetic energy of an object is how much matter it consists of and how fast it's traveling. So if either one of those increases, then obviously you're going to ultimately increase the kinetic energy of that matter. Okay, some units, guys. So you can see where we get this from. This would be in meters per second. This would be in kilogram, and that's raised to the power of 2. So you can see where that comes from. But that's how we define a joule. And we don't really use those units, but a joule, that's a typical heat unit, potential energy unit that we will use throughout chemistry. There's also an older non-SI unit. So this is used internationally, but we use obviously in the US calories. But you guys remember your food calories are actually a big C calorie. It's actually 1,000 of these small C calories. But here's a conversion that you guys want to write down, so that way we can always convert between joules and small C calories. Okay, guys, two definitions. There's what's called the system and the surroundings. The system includes molecules we want to study. The surroundings is everything else. In terms of chemistry, guys, the system will be like the reaction, and the surroundings will obviously be the surroundings, everything outside of that. Energy can also be transferred as heat, so that's a lot of times what we're talking about with thermochemistry is heat transfer. Heat flows obviously from warmer objects to cooler objects. Somebody has a warm hand, shake somebody with a cold hand, heat will flow from the warm-handed person to the cold-handed person until they reach thermal equilibrium. That is, both hands have the same temperature. You guys remember what temperature is? It's the average kinetic energy of the molecules, right? So it's so obviously the higher the temperature, the faster those molecules are moving. The lower the temperature, the slower they're moving. First law of thermodynamics, energy is neither created nor destroyed. Notice a lot of this is not even purpleized, so you don't necessarily have to write it down, but you guys, it's your choice. In other words, the total energy of the universe is constant. So, for example, let's say we have the initial state. Let's say your reactants have a high potential energy, and then you're forming products, which is a low potential energy, kind of like this. You take paper. Paper is going to react with oxygen. If we think about the potential energy, the enthalpy of the paper and the oxygen, it's relatively high, and you can tell because as this is going. You guys know what the flame is. It's just light and heat. It's light and heat energy. Where did that energy come from? The reaction of oxygen and paper. So now what do I have? I've got a lot of carbon dioxide. There's also water vapor that we can't really see. And then we've got ash. Well, wouldn't you guys agree? Wouldn't you guys, it's pretty, it's obvious that what had a higher potential energy? The reactants we started with or the products we ended with? Obviously the paper and the oxygen. Think about paper and oxygen kind of like up here, and then we produce ash and carbon dioxide down here. This had more potential energy. What happened to that, some of that energy? It was given off in the form of light and heat. So though the system lost energy, right, because energy was released as heat, if you count the system and the surrounding together, so the system lost energy, but the surroundings gained energy. If you add those together, it will always be constant. That's what we're saying is the first law of thermodynamics. And then we could also talk about heat going into a system. And you guys, I think we talked about this before, when heat is absorbed by the system. So in this case, well, this one we already know. What kind of reaction was that? It starts with an E. You guys should know it's exothermic, but that's when heat left the system. What do we call it when heat enters a system? Meaning it absorbs heat energy or potential energy from the surroundings. That is called endothermic. And then the one we're more familiar with is exothermic. Exo meaning out, okay? You know what, for time's sake, I'm not gonna show the heat flow. I try to keep these videos to 25 minutes. I know sometimes it's hard to focus, guys. So we're often measure the change in enthalpy of a reaction, and we call that delta H. So enthalpy we abbreviate with H. Remember what enthalpy is? It's just potential energy. It's how much energy that system has. Whenever we do a change, you guys, a triangle is a change, we always do final minus initial. It's like even with temperature. Let's say the temperature went from 20 degrees to 30 degrees. Well, the initial temperature was 20, the final temperature was 30. So if we want to get the change in temperature, we do the final, which is 30, minus the initial, which is 20. It's a positive 10, right? 30 minus 20 is a positive 10. That positive indicates that the temperature rose. But if the temperature dropped, let's say from 30 degrees to 20 degrees, then we say 20 minus 30, now you get a negative 10 degrees. What does the negative mean? It means the temperature declined. So in the same way, we do the final minus initial. We take the enthalpy of the products. Remember the products. So in the case of that paper burning, we would take the enthalpy of the paper, the carbon dioxide, and the water vapor, and we would subtract the enthalpy of our initial reactants, which was the paper and the oxygen. And what would we find? What kind of value would we get? Hopefully you guys would realize you would get a negative value, right? Because the enthalpy of the reactants was far higher, so I'm taking a smaller number minus a larger number, I get a negative number. And what does a negative number indicate? Negative meaning heat was lost. That's what happened as I burned the paper. Heat was lost, right, from the perspective of the system. So you can also look at it from the case of the combustion of methane. So methane reacts with oxygen, and it's going to form carbon dioxide and water. Not much different than the reaction with the oxygen and paper. And you see that reaction, when you calculate delta H, will be negative 890, meaning kilojoules. So 890 kilojoules of heat was released in this reaction. If you had 1 mole of that, 2 moles of that, it's always from the perspective of the reactant, and so you would look at the coefficients. But if you went the reverse, I mean, theoretically, you could take carbon dioxide and water, and maybe you could develop a system by which those would come together to reform methane gas and oxygen. Well, the reverse reaction, same amount of heat is involved, it's just notice it's a positive value, indicating you would need 890 kilojoules of energy in order to go from a low enthalpy state to a higher enthalpy state. Endothermic delta H is positive, exothermic delta H is negative. See, that's in purple. Delta H is called the enthalpy of reaction, or we could call it the heat of reaction. So in this balloon, we've got hydrogen and oxygen, and you guys know hydrogen is explosive or combustible. So all I have to do is initiate the reaction. I think I did this in class. Some of you guys would remember. Hydrogen and oxygen. What's going to happen? It comes together and form water. Remember, I say that's the reaction that can even, maybe a lot of cars here in the future are going to be running off that reaction, because it's quite an exothermic reaction, as you guys can see, by a lot of light and heat. So we're going from higher energy reactants to produce lower energy products. You guys will notice most reactions are exothermic. You go from a higher energy state to a lower energy state, potential energy state. I'm thinking about doing a marathon. He's saying, like, you can do a full or half marathon. He's like, Game of Thrones, yo. All right. Calorimetry, that's where we're measuring the amount of, we can't measure directly heat flow, but we can ultimately find out how much heat was transferred. So that would be the process we use to get, for example, these values. So in order to do that, we have to understand the concept of specific heat. You guys should remember that from last year. It's called specific heat, or the heat capacity. That is defined as the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Kelvin. You guys remember we always use Kelvin in, and I know in the past we've used degree Celsius, we've used Kelvin, and you're going to see it's not too different. So you'll notice and the reason why it's called specific heat, because each particular kind of matter has its own unique specific heat value. So when we say the specific heat value of iron is 0.45, what the heck does that mean? Well, you guys look at the units. What that means is it takes 0.45 joules of heat to raise 1 gram of iron by 1 degree Kelvin. That's its heat capacity. Now you guys will look, of all these, you got different kinds of matter. What obviously clearly has the highest heat capacity, which is not too surprising, it's water. So we'd say water's heat capacity is 4.18 joules. That means it takes 4.18 joules of heat to raise 1 gram of water by 1 degree Kelvin. That means water can absorb heat, a lot of heat, with minimal temperature rise. And you guys, that in part explains why, your pool, your pool could be like really, really cold. Let's say it'd be in the middle of summer, but you jump in your pool and it might still be pretty cold, because what does it have? It has to absorb a lot of heat energy from the surroundings to raise its temperature. But you'll notice these ones, shouldn't be surprising, notice the ones that have relatively low specific heat values. Notice, what are they? Aluminum, iron, mercury, guys, what are those? Those are metals. And what do you know about metals? Don't those heat up really quick? So those absorb heat, and it immediately the response is a dramatic increase in temperature. Says, what do these values mean? Give a sense of explanation. We talked about that. And what do we notice? Metals have low specific heat values. Water in particular has a relatively high specific heat value. Okay, so when we carry out calorimetry, we could use even a simple thing. I don't know if you guys can see this image, but it's a styrofoam cup. The whole purpose of a styrofoam cup, you guys know, is an insulator, right? If you're going to drink hot coffee, you'd want to put it in styrofoam because styrofoam is a good insulator. It's going to minimize the heat transfer from inside to outside, and so you could use it for calorimetry purposes. We would try to be a little bit more sophisticated than that. We'll see. You can indirectly measure the heat change for the system by measuring the heat change for the water in the calorimeter. So you guys will see with calorimeters, we often use water, and there's a reason for that. So I'm going to remind you guys of the specific heat formula. This is going to allow us to calculate the amount of heat or potential energy associated with a particular piece of matter. Q is the abbreviation for heat. The amount of heat is equal to the mass of the matter in question times its specific heat value times the change in temperature. So, for example, we'll see what happens to units. Oh yeah, we'll show that. You guys, Q is in joules. And so if you guys ever forgot the formula, you shouldn't be, well, even if you did, you guys will have a formula sheet available for you guys on the AP test. They don't necessarily expect you to memorize all these formulas, fortunately. It says it's equal to the mass. The mass would be, right, in grams, or, you know, if it was kilograms, you might have to convert that. You guys remember the specific heat values? They're in joules per gram, degree, Kelvin. We don't call it degree Kelvin, we actually just say Kelvin, but, and then times change in temperature. Well, a change in temperature would also be in Kelvin. We'll do one in particular. Okay, now look at the units. Kelvin on top, Kelvin on bottom, cancel. Gram on top, gram on bottom, cancel. Joule equals joule. You see how the units work out. That can help you, even if you didn't know the formula, you could probably derive it yourself. So here's the situation. We often use what's called a bomb calorimeter. So we could, the whole idea is, you know, like if I wanted to see how much heat was given off by the burning of the paper, I could perform that, put it in a calorimeter. So for example, we could put it in, you guys can see how a calorimeter is designed. It's got this a container on the inside, and then it's got a larger container on the outside, and it's got water here. Well, imagine if I put the paper in there and I burned it. What's going to happen? It's exothermic reaction, heat's given off. What's going to absorb the heat given off by this reaction? The surrounding water or the surrounding calorimeter. So what can I do? If I can measure the temperature change of the calorimeter, take into account and then include the specific heat of the water and how much of the water I have, I can ultimately calculate how much heat is given off. So we're going to do a practice run. Let's say, but you guys see what a bomb calorimeter, not everything would be flammable. Let's say I had an apple here. I got an apple. Okay. Obviously, I can't just, you know, light my apple up because obviously you guys know the fruit contains a lot of water, and so it's not flammable. But what I can do is put in a bomb calorimeter, and it's got an ignition apparatus that it can blow it up. Once again, you would expect the apple has a lot of energy, high enthalpy. The products are going to be lower in enthalpy. It's going to be an exothermic reaction. What's going to happen? The water's going to absorb the heat. So if I can calculate how much heat the water absorbed, that would be equivalent to how much heat or how much energy was given off by the combustion or the decomposition of the apple. So let's just make up a scenario here. Let's say I have it in a calorimeter. And technically, you would have to do this twice. You would have to take into account not only just the water, but you notice the calorimeter also contains, usually your calorimeter is like made out of aluminum or even could be copper. So you would actually have to account for the temperature change or the amount of heat that the calorimeter apparatus itself. But we're just gonna go simple, and we're gonna say in our calorimeter we have 1.5 liters of water. Okay, and we're gonna say when we put our apple in there and blew it up, it was originally, we're gonna say it was 10 degrees Celsius, and then the temperature of the water, you'd have a thermometer in there, rose up to 85 degrees Celsius. So the question is, we want to know what is the potential energy of this apple? You guys notice, right, when you buy something in the market, they have to display not so much on fresh fruit, but this has a certain amount of calories. And that's letting you know how much energy is in this food item. So I would know that's how much energy I would have to expend if I didn't want to gain weight as a result of eating this apple. So here's what we do. We'd use our specific heat formula. Okay, so I want to know how much heat is given off by the apple, so I'm going to look for the Q. And what's absorbing the heat? It's going to be the water. Like I said, in actuality, you'd have to do it twice, but we're just going to take into account the water. But you'll notice, this is a good reason why we tend to use water. When you think about water, it's very easy to remember. Well, in terms of the specific heat of water, it's really easy to remember. It's 1 calorie per gram degree Kelvin. But oftentimes we want to have it in joules and not. Oh, you know what? Let's do it in calories. Let's just make it easy. So there's 1 calorie per gram degree Kelvin. Notice I said, you know what? And if I put degree Celsius or Kelvin, it's not really going to make a difference, because if you guys think about this, look, we got 0 degrees Celsius, and we have here we're going to this. I'm just going to remind you of, say, 0 degrees Celsius. And you remember there's negative 273 degrees Celsius. Remember that corresponds to 0 Kelvin. Remember that's the lowest possible temperature. That's the point at which there's no molecular motion. This is 273 Kelvin. Well, let's say something was 30 degrees Celsius and the temperature dropped to 0 degrees Celsius. What's the temperature change in Celsius? 30 degrees. Well, what's 30 degrees Celsius in Kelvin? That's 303 Kelvin. So if I had the same temperature drop, how much did the temperature drop from 303 Kelvin to 273 Kelvin? 30 Kelvin. You guys see, temperature difference will still be the same, all right? Even though the absolute temperature is different. So the temperature change, we see obviously the temperature changed, it increased by 75 degrees Celsius. So I put, that's 75 Kelvin, right? And then the mass, so notice that's in volume, but you guys remember the density of water is 1 gram per milliliter. So if that's 1.5 liters, isn't that 1,500 milliliters? So isn't that 1,500 grams? Okay, you guys look at the units. Kelvin cancels, grams cancel. I'm left with that. 1,500 times 1 times 75. I already forgot what that is. I think it's I'd say it's about 113,000. I'm going to say 113,000 calories. So you guys remember, if I wanted to know the calories, does that mean that's how many calories are in the apple? Bang, you're like, that's a whole bunch of calories. You guys got to remember, food calories are a food calorie is a kilocalorie. So that is equivalent to 113 kilocalories, which is the 113 calories. So that's how much energy this apple has. And then you guys remember, we actually don't prefer calories. We actually prefer the international unit, which is joules. So I'd have to convert 113,000 calories. Remember, the conversion factor is 1 calorie is equivalent to 4.18 joules. So I would proceed to multiply that by that to get the joules. All right, that's the type of work you guys are going to be doing on the assignment associated with this lesson. We'll see you guys next time.